Alrighty, it is 10:20, so let's get started, everybody. So I've posted the announcements here for a few minutes, so hopefully those of you who've already joined have read through some of it, but let's go through all of the announcement points together. The first and most important point, mainly because today is the deadline, is the pass no pass deadline option, and that you have this option or to opt in today until 5 p.m. Eastern Standard Time. And OSU guidelines have dictated that a passing grade is a grade of D or higher, a letter grade of D or higher. Today, there's also a withdrawal deadline. And so there, of course, the W will show up in the transcript, and that deadline is today as well. Now, I've been announcing this, but I just want to reiterate for the last time that your Carmen gradebook is updated. So their scores should be weighted. You should be able to see that. It's weighted in terms of the exams being 35% of your total percentage score, and exam 1, 2, 3 are now weighted 20%. The extra 5% is just for so that you can weigh exam 1, 2, or your hypothetical exam 3 grade. So we shifted it so that it can be flexible, so that way that extra 5% can be applied to whichever exam you score the highest on. So that way it takes away some of the high stakes levels. Exam 3, which is also cumulative. So hopefully that bumps a lot of the students right at the borderline between 2 letter grades up, where in which it could make a difference. Okay. But the letter grade as they pertain to the total percentage scores that has been available through the syllabus, and it's also on the Carmen syllabus page. So please check that out and remind yourself of that conversion. And point 5, the grade deadline has shifted. Obviously, it was due within, for graduating seniors, it was due within 24 hours of the final exam, and there was a certain date, and a lot of you expect the scores as well as letter grades to be posted within 24 hours. OSU has changed that to now both graduating and students who are not graduating. Your deadlines are going to be the same now for grade posting. That's May 8th. Obviously, the final exam is May 27th to April 27th to April 28th. So we anticipate that we should be able to post earlier than that date, but obviously we would not post any later than that date because we wouldn't want to negatively affect anybody's graduation requirements. Right? But rest assured, we will post the grades in time. And something to note, also as of April 10th, OSU has automatically added passwords to any Zoom recordings through the cloud, and that's how we've been doing it, so that it offers the chat feature posting and the aggregation of the lecture, the shared screen, and also the scrolling questions in the chat. They do make exceptions. We can remove the passwords, and so if you try to access the recording from April 15th, you will notice that you needed to input the password. That password is in the link on the Carmen lecture recordings module. But I've also now taken that away because you're also automatically alerted when the recording is available, and that link doesn't give you the password. And so because we safely distribute the Zoom recording link, or the link to the recorded lecture only through Carmen, of course, Carmen requires OSU authentication. We only require you to put in your password once, and so if you click on that link, that's distributed through Carmen messaging or the link on the Carmen module under lecture recordings, then you should be able to bypass it without a password. But please let us know if that is still a persistent problem, right? It's one fewer password to put in because there's already a layer on a protection on top of that. And so these are added security features that OSU has enacted because, of course, there have been some concerns about Zoom security features. Okay. All right. So I'll pause there. Are there any questions thus far about the announcements I just made. Okay. Well, I think sufficient time has passed. So we will go on and continue with failure analysis and fatigue before we start corrosion, which is the last module of this course. Sorry, it's not the last module. It's the last module that I'll be giving. The last module, Professor Glendane will guest lecture. He's been in material science for a long time. He's a huge expert on manufacturing, and so he'll wrap up with the societal impact of materials engineering. So I think it'll be a really good lecture, and he's been leading the huge efforts in academia as well as industry on manufacturing and how to take all of these components that you just learned from material science, from sourcing to atomic, solid solution strengthening to cost analysis and manufacturing, all of that. And so he'll talk about all of that. I think it'll be quite a treat, his lecture. So, okay. So with that, let us proceed to failure analysis and fatigue. Okay. So I want to just kick off the continuation by doing an example. So here we have an aircraft component in which the material has a K1C of value of 26 MPa root meters, square root meter. It has been determined that the fracture, results at a stress of 112 megapascals when the maximum or the critical internal crack length, so this is important, it's an internal crack of 9.0 millimeters. And if you take the same component and alloy, and you're asked to compute the stress level at which a fracture will occur for a critical internal crack length of 4 millimeters. So you're given a lot of numbers here, and also some materials property, which is the plane spring fracture, fracture toughness of 26 MPa root meters. So what you're thinking is, well, I don't actually know the geometry of, or the geometric parameter of this internal crack length, and so I have to go figure it out, right? It's the stress intensity that's pi, is y times the applied stress times the square root of pi times A. A is the crack length. So if it's a surface crack and you're just given that crack length, so if it said surface crack length is 9 millimeters, then we would keep it at 9 millimeters because that's the length that's defined for the surface crack. This is an internal crack, so we actually have to divide that value by 2. Okay, so we know the applied stress is 112 MPa. We know that fracture, so that means if your stress intensity factor is greater than your fracture toughness, there will be fast fracture. So we know then, okay, well, I know what K1C is, but I don't know what Y is. I don't know what the geometric factor is right now. I mean, if that were given, let's say if it's a simplified, system, then simplified geometry, we can say, okay, well, assume Y is 1 or assume Y is some value. But here we don't actually know what it is. So the first step is to go and figure out what it actually is. So there we can rearrange this equation to get Y. And so that's just, we know fast fracture will occur at when it's K1C or the stress intensity factor is greater than K1C. So basically, I've just rearranged the equation to compute the geometric factor. And so Y is then K1C is 26 MP. This might reduce the. divided by the applied stress, which is 112. Oh my. Today, the tablet. Pi times, the internal crack length is 9.0 millimeters. So that's really 9 times 10 to the negative 3 meters divided by 2, okay? Because it's the internal crack. So computing that, we get y of 1.95. That's the geometric factor for this internal crack. Now, for the same component in alloy, we're asked, now that we know the geometric factor, compute the stress level at which fracture will occur for a critical internal crack length of 4 millimeters. Once again, internal crack length, so we know that the crack length A that we should use should be divided by 2. So now we need to figure out what the stress level is for this critical crack length. K1C divided by Y. So here we have 26 MPa per meters. Y we know is geometric factor. Pi, this is a new crack length. So 4 times 10 to the negative 3 divided by 2 meters. And that gives us the stress in which fracture will occur for this critical internal crack length of 4 millimeters is going to be 168 megapascal. Okay. Okay, let me check. Okay, so there are 2 questions thus far. What is a square root term in the numerator? Oh, that's the unit. Why do we sub in K1C for K? So K is a stress intensity factor. Why do we sub in the plane strain fracture toughness for that? Well, we know, I'll scroll back. Go back easily. Right. We know here that, go all the way back. Yeah. So we know that this is stress intensity factor we can compute based on the applied stress and the critical crack length, or the crack length. And so if it's greater than that, then the cracks are not stable and that fast fracture will happen. So that's what this question is asking is, when does this occur? So now we can say, okay, well, if we know what the fracture toughness is, when it's right at that critical crack length, then fast fracture will happen. Okay. Will content from the guest speaker lecture be on the final exam? Well, does that dictate if you're going to show up? Given that so yes, on your syllabus, it is, because the guest lecturer will be lecturing on content that has already been dictated, will be covered. So it has been on the syllabus. So instead of my giving the lecture for that module, the guest lecturer will be giving that content. Now, we've coordinated so that obviously the guest lecturer knows the content, what should be covered. But the whole point of having a guest lecturer is that this person should add something, right, beyond just the content that you could read from a book, right? And so Professor Glenn Bain has had 30 plus years in material science and engineering in academia, but he's also worked with a number of industry partners. He still works with them, and he's really been a leader in manufacturing. And so he'll speak to his collaborations with a number of automotive collaborators where they tackled a lot of the materials design concepts that are based on the fundamentals that you've learned here and maybe in some of your other classes as well. And so who better to speak about the societal and environmental impact than someone who's been in this area for a really long time and can speak to the progression and the evolution of how we do material science and engineering. Okay. So fundamentally still rigorous, but this person adds many years of experience. Yeah, so the next question is there a difference between KC and K1C? Yeah, so K1C is a subset of KC, right? K1C, not the number one, but the Roman numeral one. So it's spelled out as this Roman numeral, even though we speak colloquially as K1. And that's to indicate how this how the material is breaking. So here are some of the modes. So K1C is denoting that it's operating in mode 1. So the plane strain fracture, it takes into account this tensile mode of crack propagation versus other modes that can be more complex, such as this sliding mode. There's also a mode 3 in which you get a different type of a fracture. So for this class, we're just concentrated on mode 1, which is opening in the intention. Okay. Oh, let me just make sure. Plug this in. Okay. My video might be disconnecting in a little bit. We'll see. Okay. All right. So let us continue on. So we are not concerned about mode 2 or 3 for this class. That is correct. All the examples have been on K1C. So we're ignoring 2 and 3 for this class. That is correct. That means, what does that really mean for you? That means it won't be on an exam. I hope that is very clear and alleviates some stress and concern about that. Okay. So where we left off was on creep, actually. And so, well, actually, I skipped by this slide, mainly because there was a lot to talk about and not enough time last time before interruption and being interrupted in midway through this thought. But basically, when we were talking about fatigue life and how crack propagation can actually happen, when you form a crack and then this crack gets bigger and bigger, it's actually not a linear rate. Well, that actually depends. Here it is a linear rate, but in the beginning, if you look at the crack and also fatigue life, so dA over dN, the corrosion and fatigue folks know this inside out. But basically, there are 3 regions once you have initiation of the crack formation and then propagation of the crack. And so we talked about the three regimes in which it can happen, or the 3 stages in which this can happen. But the takeaway message is this should be a huge concern for you as it gets near the fracture point. The crack propagation accelerates, and so you can see here the crack rate formation, dA over dN, the number of cycles in which it happens. You see that it accelerates quite a bit. And so it's a real concern if you initially have a crack. We said before, okay, cracks can be stable if they're of a certain size and you can apply a certain load and it won't actually propagate, right? It's nowhere near the fracture toughness point. And so it's fine. It's going to be stable. The material can still be used in service. It's fine. The story changes quite a bit. The number of cycles, that fatigue has happened. And also, so if you're here, that might be fine. But as you get closer and closer to KC, it might not actually be so fine after so many cyclic stresses. So here you see it's plotted versus log K, right? So this is not a linear scale. Sorry, log of delta K, and delta K is just the max minus the min. And so where do you get these values for max and min? Well, this is a little bit maybe more granular details than you were anticipating. But when we were calculating the stress and intensity factor, right, we said it was it was dependent on the crack length and also the applied stress and the geometric factor, which usually is some low, number. But here now you have to take into account, which maybe delta, something like that. So if your now applied stress is cyclical, you have some max, you have some min, you now have to take that into account to calculate the acceleration of crack propagation as it approaches your fracture toughness. Okay. So once you get into the real world and you are actually, engineering materials where lives are at stake, this is actually something you really need to predict well and do safely. One of the other things that I did not mention due to time is that when we're looking at fatigue life and fatigue life testing, and we're looking at the stress amplitude versus number of cycles to failure, so SN curves, when we talked about this, what I didn't talk about is the spread in the data. So here, when we're measuring the stress amplitude as a function of N, the cycles to failure, the data points kind of spread out like this, where, when, let's say you take one specimen and you apply some max stress and some min stress, or sorry, you apply some max and some min, and you get, okay, number of, this is the stress amplitude after this number of cycles. So you do that a number of times to get to statistical significance. What happens is then you plot this data and the data starts to look like this. And the red is sort of the error bars. Okay, your error bars get bigger and bigger as N increases. So what does that really mean for you as an engineer? It means that if you have some high stress amplitude, the failure, the number, you can compute the number of cycles to failure more precisely. As that increases, as N increases, since your error bar is larger, you cannot really say as definitively, if it's going to fail after this number of cycles, which means if you're the manufacturer and you're saying, I can guarantee my part up until this number of cycles, it's really this number of average cycles plus or minus this. So it could last a little bit longer before failure, and it might not, obviously. So what you really want to be sure is the spread in your data and how confident can you be when you put this part in service. Okay, so that's a really key point, that this curve is extremely useful, but the caveat is you must look at the spread in the data analysis and your standard deviation as you go on. So anyway, just a point for safety. Okay, so let's then talk about creep. We talked about that. So Right, so this is just a review on dislocation and how dislocation can travel and climb to different parts of the material. So I just wanted to wrap up creep with talking about safety prediction. So when we talk about a static applied load at elevated temperatures for some period of time T, we really want to know when is it safe, when is it not safe, right? I mean, that's ultimately the question we want to answer at the end of the day. And so creep is an Arrhenius type of process. And as you recall, we've come across quite a number of these processes that are thermally activated, such as, vacancy formation. We've seen this in excitation of electrons. We've seen this for a number of systems. And so creep is no different. So the strain rate, so this epsilon dot, is a strain rate, and that's dependent. It's thermally activated. So at 40% of the melting temperature or higher, you can imagine that creep can happen quite readily, and it increases. The strain rate increases as a function of temperature. So as you increase your temperature. And so what people have done is they've used this Larson-Miller parameter that takes into account all of these conditions, right? So what time to failure, what temperature you're at, the applied load, and so that's also assumed in this Larson parameter. So when you recall, when we were calculating, how many vacancies can form, right? It's lower, the number of vacancies that can form are lower for lower temperatures, and then instead of just dealing with exponential equation, we plotted the Arrhenius dependence as as conductivity, or y versus a 1 over t. So here, this is no different. It's also the same thing where we take the log of both sides, and basically what it can tell us is the amount of strain, the amount of stress that's applied versus this Larson parameter that takes into account T, the time to rupture. If you're in this regime and you're reading this plot, that means it's safe to operate under those conditions. And then above that, of course, is the material is going to experience failure. And we're not going to go into great detail, mainly because the derivation of creep with the Larson-Miller parameter and all of these is a little bit more involved, but that's, I wanted to talk about some of the takeaway. Okay, so let's review before we move on to corrosion. So what is going to cause failure? When is a component going to most likely experience failure? Well, you need to know the stress level, you need to know the fluctuation max min if it's cyclical, and also stress concentration due to the design or the flaws in your material. Of course, all materials have flaws. It's just how do we design a component in a way that in which we can still operate safely even when we have those flaws at a certain temperature. Okay. So when we're thinking about fracture, we're taking into account the crack length and also when it grows. So is the applied load less than the tensile strength for ductile material? Is it lower than the yield strength for brittle materials, right? And so there we talked about the fracture toughness, fatigue, cyclic crack growth. So when we talk about, when we apply a max and a min, in tension and in compression, how does that affect the number of cycles to failure, NF? How does that affect the crack propagation? Which stage is it in? And then we also talked about creep where we applied a static load, but then we hold it over time. And so there we need to know some activation energy and also this materials dependent parameter. This obviously we won't be focusing on too much, but I thought I included in the summary for completeness. So are there any questions before I proceed on to corrosion? Okay. All right. I think sufficient time has passed. I'm going to take that as a no. No questions for now. Interesting. Let me exit out real fast. All right. Fascinating. Okay. Well, one moment, folks, while I figure out why this has decided to cut off parts of the screen. Let me stop sharing and reshare again. Okay, that's much better. Let me switch over to this side because the camera is being wonky. That's okay. All right, so slightly different angle, but the video will continue. Okay. Right, so corrosion, the last module from me. There we go, this is better. Okay. Sorry, everybody. Right, so the last a module from me. We're going to bring it all home and talk about how does corrosion tie into with failure analysis and fatigue. So after this chapter, you'll be able to master some key terminologies, which is, oxidation and reduction. You may have heard this already in your general chemistry course. So we'll review what reduction and oxidation means in electrochemical reactions. We'll also talk about galvanic couple, standard half cell, the standard hydrogen electrode. We'll talk about cell potentials and also the what happens when you have two pure metals in solution together. And then we'll also talk about the rates in which this happens, oxidation and reduction happens. We'll also talk about corrosion in the sense of environmental assisted corrosion. So what happens when your material is in, some corrosive environment, like in acid, HCl, or in seawater, things like that. All right, and we'll also talk about polymeric corrosion, although that's not really a thing in the sense that you need movement of electrons, and so polymers can degrade, but in terms of the definition of corrosion and how you need to move electrons around, that's more prevalent, obviously, in metals, right? But you can have degradation in polymers. And there is some wear, even though they're more, polymers are more corrosion resistant. Okay, so why do we even care about corrosion? You can imagine that it's a huge billion-dollar industry to prevent corrosion. And you can see this especially in Ohio, where we have winters, right? We have to salt our driveway, we have to salt the street, and that could assist with corrosion of metal parts in your vehicle. It can also cause major issues in aircraft. And so here on this slide, you see data tables that talk about how failure has happened in planes, right? So this comes from a decade study from Scholes and coworkers. This is 2009. That means 10 years before that, they've looked at airplane parts and also aerospace components, and they looked at what was the original the original reason for failure in a material, and you can see here they've summarized it as as 80% of the initiation feature was due to corrosion pitting. Okay, and so we'll talk about what is that versus like uniform corrosion. But it's a huge problem. So if you understand corrosion, you can prevent potentially or catch before these issues happen. And so within that, what type of corrosion are we talking about? Are we talking about exfoliation of some of the material off of the main component? Are we talking about corrosion fatigue? Are we talking about in-plane cracks? That's something we just learned about. Are we talking about bore corrosion? So there's obviously different type of corrosion, right? There isn't like one mechanism by which material, these metals are being etched and oxidized, right? And so understanding all of that can lead to a lot of cost saving, billions of dollars, and it obviously on top of that, if it's aerospace or aircraft, right, then that will also lead to saving of lives. Right, so there's real world impact there. So what we're really talking about when we talk about corrosion is we need to break it down into both the thermodynamic part and in the kinetics part, right? When you have a metal and when you're mining it out of the ground, most likely you're not going to find a piece of aluminum. You're not going to find a sheet of aluminum foil, right? You're not going to find a huge piece of iron. Usually it's in an oxide form, which then metallurgically you need to convert that into iron. So let's say from iron, or typically you find it as iron oxide, and then through refining, casting, rolling, shaping, all of that jazz, right? You get out all the parts that you want in metallic form. And same thing for aluminum. Typically you find it as aluminum oxide. Lithium in lithium ion batteries, you don't just find lithium in ores, you find it typically as lithium hydroxide, and then you have to convert that, or lithium carbonate, and then you have to convert that ion into a metal. So when you buy lithium metal chips from, or lithium foil from the vendor, it has been converted from the ore, right? So all that means is we're fighting against thermodynamics. Typically, when you use aluminum like this, right, it really wants to oxidize. If you look at the Gibbs free energy, and we talked about that, where we talked about imperfections, right? Delta G is equal to delta H minus T delta S, right? So there's an entropy term, and there's also an enthalpic enthalpic term. And so the takeaway is, if the Gibbs free energy is negative, what that's telling us, of course, is that it's most likely going to happen. It's thermodynamically favorable. So for aluminum to go to aluminum oxide, this corundum, thermodynamically, that's going to happen, right? So really, we're fighting against thermodynamics when we want to keep something from corroding, when we want to keep something in its metallic form. Okay? And so if, let's say, you're a car manufacturer and your F-150 is entirely, the entire chassis is aluminum, say, this is something you are heavily concerned about, right? Obviously, you're concerned about the mechanical properties and how it can, the toughness of the material can absorb a lot of energy upon impact. So if there's a car accident, your car will sort of crumple, but not, disastrously fail. But on top of that, now you have to consider, fighting corrosion in the Ohio winters then. Okay. All right, so let's also define what corrosion is. Before already, I was starting to go into the details of what corrosion is. When polymers undergo corrosion if they're not transporting electrons. If you've taken the new bus shuttle within the last year or so, one of the stops is Fontana Labs, and that is named after Mars Fontana. And Mars Fontana did many years, decades worth of fundamental research on corrosion. And he has defined it as deterioration of a material because of reaction with its environment. Then the Department of Defense, so the Undersecretary of Corrosion, the Undersecretary of Defense has defined corrosion as the deterioration of a material or its properties due to a reaction of that material with its chemical environment. Okay, now we're talking about not just deterioration, right? Because you can have deterioration, but what kind of environment are you just applying pressure? Is it what is it? So now there's an extension to, we have to take into account the chemical environment, right? Is it an acid? How corrosive, how acidic is this environment, that sort of thing. And then of course, there are other professors at Ohio State Materials, such as Professor Gary Frankel. And here I've taken an excerpt out of Professor Locke, where she has said, and they both work on corrosion related research, where she's talking about corrosion as deterioration of a conductive material, typically a metal, through its interaction with the environment. So keeping with the defense definition, with the environment in a process that involves electrochemical reactions. So by this definition, polymers would not corrode because they wouldn't undergo these electrochemical reactions, and they're not conductive, right? So depending on which definition you follow, if you just use Mars-Fontana's definition, deterioration of a material of a reaction with its environment, then that could happen to polymers. But if you use this definition, then polymers would not corrode, right? So we'll go with this and talk about, well, it's all based on all of this. So we're not ignoring the history. We stand on the shoulders of giants, right? Whenever we, as scientists and engineers. So we don't ignore the history, but we evolve and expand our definition, right? Okay, so what are the mechanisms that are involved in corrosion? So corrosion occurs via two coupled electrochemical axial reactions, right? So how are they coupled? They have to be coupled electronically, right? There has to be a pathway for the electrons to travel, and they also have to be coupled ionically, right? They have to be in the same solution. They can't be isolated from one another. So they have to be coupled. And a typical electrochemical reaction is a type of redox, so reduction oxidation reaction that involves, for example, these two reactions. So here for aluminum in water and iron in acid. So the aluminum here becomes oxidized, so that's the anodic reaction. Here's another example where you have iron going from iron 0, so the metal is always 0 valent, but you already knew that, right? It doesn't have an oxidation state because it's 0, or its oxidation state is 0 valent, and then it becomes aluminum 3+, right? Or iron 2+ in this case, because chloride is 1-, so Cl2 makes it 2-, and so iron is 2+. Okay, and what you see here is that there's an evolution of hydrogen. So what's happening there is hydrogen here is 0 valent. H2O though, H is plus, and that's going to H, right, 0 valent hydrogen in H2, right? So really what's happening when we write this out is we're writing that iron plus 2H plus 2Cl- goes to this, right? That if we had to write out the ionic form of all the charges and oxidation states, this is what it would look like. But obviously, what we really write is this final equation, okay? And so here, we define, let's go back to these two examples, we define the anodic reaction where oxidation is happening as the oxidation where iron is going from 0 to 2+, aluminum is going from 0 to 3+, and then the cathodic reaction where you have the reduction of H+ with 1 electron going to now H0. Okay. So if we have, let's say, this overall reaction, the anodic reaction, it's just Al going to Al3+, right? So very similar. This would be the anodic reaction. So the Al going to Al3+ plus 3 electrons, because what you need is charge balance. Okay, so where do these 3 electrons go? Well, let's put them here for now. Okay. So very similar to this. Instead of 2+, you now have 3+. So then the cathodic reaction is just H+ going to, it's just going to that. But obviously we need to then charge balance that. Okay. So then what's really happening at this interface? Well, let's say here you have this metal, the electron conductor. It sits in some electrolyte. So in the case of this example here, it's just sitting in H2O. Okay. And how we treat this molecule is actually it's H plus and OH minus. And so what's happening is then during the electrochemical reduction, oxidation, aluminum is becoming Al3 plus. And it's going, that Al3 plus is then going into the electrolyte. The electrolyte typically, some salt in a solvent. Here we don't have any salt, we just have water as the solvent. And so what's happening here is when that happens, you see that the H pluses, they end up here, they interact, right? They're everywhere in the electrolyte, but the ones that are at the interface here, they'll see other H pluses and they'll react to form H2, and that will evolve. It's a gas, so it will evolve. And the Al3 plus goes into solution. It actually dissolves. This ion dissolves in the electrolyte. Okay. So that's one part. So what happens when you have, let's say, two materials? So one material is going to be susceptible to corrosion. We'll talk about in just a few slides, what makes one material more or less susceptible, and that has to do with its voltage when we're doing all these tests. But when we talk about a corrosion cell, we need to define the anodic reaction site. Where is that happening, right? That's happening right here. And then we need to talk about, so that's in the green area. Then we also need to talk about, well, where's the other half cell? Where is the cathodic reaction happening? And the cathodic reaction in the cathodic site is also happening at the same place. They can be right next to each other, right? And so we see that in these purple areas right here. So the cathodic, where H plus is combining with another H plus to form H2 and evolving, it can happen right there at the same interface. And then there needs to be electrical conductivity. So here it's just a metal in water, right? A piece of metal in water. What happens when you have two dissimilar materials, let's say iron and aluminum, or aluminum and magnesium, right? Then you have two pieces of metal and they have to be connected electrically. There needs to be a conductive pathway between the two of them. And then and the ions have to flow, as I mentioned. So the electrolyte needs to allow for ion flow. So if those four things are met, then you can have a corrosion cell. And so what causes corrosion? Well, real materials cause corrosion by the sheer fact that they're imperfect, right? All materials are going to be imperfect in some way. Even when you make, the most beautiful single crystal silicon, right, out of the Tchaikovsky method, which is something I bring up a lot because that's heavily used in industry. Even if you make the most perfect single crystal, we've calculated the number of vacancies, in this perfect single crystal, and even though you try to prevent all of these things, most materials are not the beautiful single crystal of silicon, right? I mean, they're usually polycrystalline, or they're formed into some way, or if you introduce defects to strengthen the material, right? So what typically happens in real materials, right, if it's polycrystalline, you're going to have grain boundaries, and these contribute a lot to corrosion because corrosion can happen right at the grain boundary. That can be your cathodic site. That can be your anodic site, and so your cathodic site can then be just in the grain itself. So that can happen, just the sheer fact that you have a polycrystalline material. If there are vacancies, if there are those defects, if you have adsorbed ions from solution, because you cleaned it in a certain way, you maybe heat treated into sort of gas, maybe there's some adsorbed elements that are on there. This is a huge problem with embrittlement. If you have hydrogen or nitrogen around, that can adsorb and then cause and then start to diffuse into the material, and that can be a problem that will cause, well, one, fatigue and corrosion. There can also just be dislocations. We talked about distributed dislocations. So basically, any impurity is going to, wreak havoc on your system and allow for corrosion to happen. And you can have uniform corrosion. So this is, sort of across the board, or all your sites are sort of evenly distributed like this. Then you can also have corrosion where it pits. So basically, you have these voids that can form due to non-uniformity in the material. And interestingly, you can use that to your advantage. You can use it to dealloy a material, let's say. So if you have copper and copper, magnesium, something like that, you can etch away, or silver and magnesium, whatever, what have you. What you can do is you can make that alloy, and then you can etch away you can corrode away the magnesium, say, and then leave these pits. And you can design it in a way that if you can preform the magnesium with certain configurations, with certain geometry, how it's distributed in your alloy, then once you dealloy it through a corrosive mechanism, what you get left over is, copper with all these really interesting, like, pitted structures like this. And that is actually quite useful for those working in the battery industry, because then you can basically put your active material, your cathode, your positive electrode material, into, let's say, these current collector electrodes, and then you can basically enhance, efficiency and charge storage. And there's a lot of, research and engineering that is involved in all of this. So corrosion is not always a bad thing. Corrosion by design is not necessarily a bad thing, to be qualitative and colloquial. It can be done in a way in which you can design it to your benefit. Okay, let me pause real fast and take a look at the questions. I think some of them popping up. Let's see. Corrosion has a direct correlation with magnetic properties. Loss, gain of magnetism, or strength of magnetism. There is no direct correlation. Like, if I had a material that I said is magnetic, that doesn't necessarily mean anything when it comes to corrosion. Now, if I were to introduce other terms that could help with that, that would inform my predictive behavior for corrosion, possibly, right? So if I know iron, use of iron, the concentration, yes. Now, maybe you're referring to the way people detect fatigue and failure, and if something's going to corrode. There are magnetic particles that are involved, if that's what you mean, but I'm not sure. So I'll pause there while I go to, so Tony has just entered an answer. There are many methods of imaging that can give lots of information. Oh, yes. So that does take into account the magnetic properties of the material that you're imaging. But just because a material is magnetic does not say anything about its corrosive behavior. How do they measure corrosion pitting? I see. So that was Tony's reply to that. So one, you can just take a look. You can also do microscopy to take a look at that. So you can do scanning electron microscopy. You can basically destructively etch away a surface and take a look at that. So there are a number of imaging techniques that are both non-invasive and invasive. Yeah. Any known strategies? Yep. So I think we answered that. There's also X-ray scattering and all of that. And you could basically reconstruct your image, your component through X-ray microscopy, electron microscopy, diffraction, and also correct the magnetic imaging. Oh, there's a clarification question. Does corrosion equate to loss, gain of magnetism? Well, sure. If your material happens to be magnetic and you're losing ion, right, then yes, by just sheer counting of atoms, yeah, absolutely, you could have that, yeah. If you're losing material, you will lose the magnetization in that material, if it's specific, right? As in, like, if you normalize by the mass of that material. Okay, so we are going to pick up here next time to finish up corrosion. So if there are no other questions, I will adjourn.
At the beginning of the lecture, you were saying some stuff about the grades that I missed. Can you go over that again real quick?
Okay, so the question was something about grades. Can you go over that? And the answer is yes. Oh, there we go. So that was in, you're talking about this, right? This is just a repeat. So if you missed it, don't worry. I've already talked about it in the previous 2 lectures. It's just to reemphasize that Carmen gradebook has been updated so that you can put in your hypothetical grades for 9, 10, 11, and also, homework 9, 10, 11, and exam 3. And the lowest homework grade should already be dropped in Carmen. So when you put in all your hypothetical homework grades, it should drop the lowest score and compute your homework percentage out of 35%. Does that clarify your question?
Yeah, I guess when we first looked over this and I quickly read this slide, I guess I thought that maybe there was like a changing to the grade scheme or something, but I guess not.
No, we would never do that to you unless it benefits you. So we did change the grading scheme for exams in the sense that the extra 5%, it was exam 1 is 20, exam 2 is 20%, exam 3 is 25%. And so to reduce the high stakes of, cumulative final exam 3 being weighted the most, which is 25%, we've given you the option, although it's just automatic, we've given you the option to shift your 25% to weigh exam 1 or exam 2 if exam 3 is not your highest grade.
Okay, cool. So we can just pick which one of the 3 gets the 25% weight.
Yeah, and in fact, you don't have to pick, it's automatic. So
okay, cool.
Your TAs and the instructors will go in after exam 3 has come in, after that score has come in, we look at which score is the highest, which exam score is the highest, and we automatically apply it. So you don't even have to opt in. You should go in and make sure we didn't make any clerical mistakes, but it should be automatic. So you don't have to say, oh, my exam 1 was higher, can you apply it to that? Or exam 2 was higher. Or if exam 3 is the highest, can you just keep that? No, it will be done automatically by the team.
All right. Thanks.
But you should go in and check it just to make sure, Yeah.
Sure.
Yeah. Any other questions?
With that being said, do we put our exam 3 score in the exam 3 portion and in the highest score in the high score portion?
Mm-hmm. Yes. So right now, exam 3, in the way it's inputted into Carmen, yes, it is only 20%. So then you would shift the 5% to, let's say you get 100, you would put in 20% and 5%, right? 20% into exam 3 box, and then and then the 5%, you give yourself the entirety of that 5%. That is correct. Yeah. Oh, you have a nice day as well. Okay. If it sounds like there's a pause, so if there are no other questions, I will sign off. Okay. Have a good day, everybody. See you next time.